have worked out a few problems on unsteady flows so far as first law of thermodynamics is concerned, and we will continue with a couple of more problems of that kind to give you a more comprehensive idea of problem solving. So, the next problem, which is problem number 13, is something like this. An insulated spring loaded piston cylinder as shown in the figure is connected to an air flow line flowing air at 600 kilopascal 700 Kelvin by a valve. Initially the cylinder is empty and the spring force is 0. The valve is then opened until the cylinder pressure reaches 300 kilopascal. Now some relationship is given between the internal energy inside the cylinder and internal energy of the line. Find an expression for T2 as a function of P2, P0 and T line with P0, which is the atmospheric pressure 100 kilopascal. You find what is T2. So, this is also a tank filling problem, but you know this is not a rigid tank, this is a variable volume tank. So, this is more involved than the tank filling problem in a sense that because volume of the trapped air within the piston cylinder changes, there is a work done associated with it, which was not there for a rigid tank. That makes this problem different from a traditional tank filling problem. So, as we have considered earlier, so we will draw a schematic. This is the piston and it is spring loaded. So, this is the gravity, it shows that you know the weight of the piston is not important because it is the piston is not aligned in the cylinder is not aligned in the direction of gravity. Okay. So, let us see the what is given and what is not. So, this is I, the property which is coming out coming in. So, I am writing I here, you know, not here. Why? To be technically correct. See, it is given that for the state I, the air supply line pressure is 600 kilopascal. If we put I here, there is a pressure drop. So, pressure is no more 600 kilopascal. In terms of enthalpy, it does not matter because this is treated as an ideal gas where enthalpy does not depend on pressure, but depends on temperature. So, enthalpy here is same as enthalpy here, and you know, so temperature here roughly same as temperature here if it is an ideal gas. For enthalpy it does not matter anyway whether it is ideal gas or not, for temperature it matters because if enthalpy here is same as enthalpy here, temperature here is same as temperature here provided it is an ideal gas, you know, otherwise not. So, then so this is air supply. So, Pi, even if it is not required, let us write Pi 700 Kelvin. Initially the cylinder is empty. So, M1 is 0. So, the control volume is the gap between the piston and the cylinder, the air within that. So, it is no more a control mass system despite being a piston cylinder arrangement. So, piston cylinder arrangement by default is not a control mass system. Here it is not a control mass system because of continuous mass supply, the mass within it is continuously changing with time. So, M1 equal to 0 and P2 is 300 kilopascal. What is also given as U2 is equal to Ui plus Cv into T2 minus Ti and Hi minus Ui is equal to Rti. P naught is 100 kilopascal. So, initially although the mass inside is 0, but there is a resistance pressure same as P naught to keep this in equilibrium. So, let us write the first law for the control volume, for the control volume. First, mass balance. So, M2 so Mi you have some Mi, there is no Me, there is no M1. So, M2 is equal to Mi. Then we will apply the first law for UF, uniform state uniform flow. Okay. Let us see what is the situation for heat transfer. It is told that this is insulated, right, insulated piston cylinder. So, to schematically represent that, we may show a insulation here. So, this is 0 because it is insulated. Then there is no M2 term 0, there is no Me term, this is 0. Oh, there is no M1, sorry, very sorry, there is no M1, right, initial is 0, right, plus M2 is very much there is no M1. Okay. So, then your usual neglect in changes in kinetic energy and potential energy will work for this problem as well. So, you are left with Mi Hi is equal to M2 U2 plus W, right. Now, a key question, what expression we will substitute for W? Can we write W as integral PdV from state 1 to state 2? Yes, we can write. Some students develop a false idea that integral PdV is valid only for a control mass system. The reason is that it is derived first by taking an example of a control mass system, but it is just work done for a moving system boundary for a simple compressible pure substance undergoing a quasi equilibrium process. Whether the system is a closed system or open system, that is not under the jurisdiction of this. This simply follows from the resistance force times the displacement integrated. Okay. So, that essentially means that you can use here PdV, and because it is a linear spring, this for a pressure volume diagram will be linear. So, the area under the PV diagram is area under a trapezium. So, this is eventually half into P1 plus P2 into V2 minus V1, right. Okay. So, now P1 is same as P0 and P2 you do not know, V1 is 0 and in place of V2 you can write mass into specific M2 into specific volume at state 2. So, let us see how we can write this. Mi into Hi is equal to M2 U2 plus half into P0 plus P2 into M2 V2. Okay. Then it is just algebra. I mean your problem solving is complete here. So, then what is given here, you just try to write in place of Hi you write Ui plus Rti, right. So, in place of Hi Ui plus Rti and Mi will be same as M2. So, you have M2 into Rti is equal to now M2 into U2 minus Ui. U2 minus Ui is Cv into T2 minus Ti. So, M2 Cv into T2 minus Ti plus half P0 plus P2 M2 and V2 is RT2 by P2, right. M2 gets cancelled from all the terms. So, that gives you an expression for T2 in terms of Ti, right, that is what is asked. So, you can write T2 into P0 plus P2 by P2 into half plus Cv is equal to R plus Cv into Ti, right.
There is a R multiplied with that P naught plus P2.
There is an R here, right, P naught plus this into R. Okay. So, then you can I mean, so this is the expression where you can substitute all the relevant values and you can get what is T2 as a function of Ti. So, the answer to this problem is T2 is 773.7 Kelvin. Okay. So, we will work out one last problem related to this before we move on to a different chapter. Problem number 14. A 2 m³ insulated vessel shown in the figure contains saturated vapor steam at 4 MPa. Okay. A valve on the top of the tank is opened and steam is allowed to escape. This is a tank emptying problem, but not for ideal gas. During the process, any liquid formed collects at the bottom so that only saturated vapor exists. So, this sentence tells that the exit state is saturated vapor state. Calculate the total mass that has escaped when the pressure inside reaches 1 MPa. So, initially pressure was 4 MPa, the pressure is released as the valve is opened and eventually the final pressure is 1 MPa. So, you have to find out what is the total mass that has escaped. So, we will work out this problem as per our practice. We will draw the schematic in the board. So, this is a rigid vessel. Let us write what is given. V is equal to 2 m³, state 1. So, fluid is water, state 1, x equal P equal to 4 MPa, x equal to 1. State 2, P equal to 1 MPa. Okay. Then in state 2 you have a, so see the physical situation you have to assess. Initially there is vapor, now vapor is exiting. So, then the energy state of the system is going down and that is reflected in terms of that vapor now getting converted to a two phase mixture, liquid vapor mixture. So, state 2 will be associated with some quality value. So, x2 is there, but you do not know what it is. So, there is a state E. Here again you have to make an assumption. So, initially it is 4 MPa, finally it is 1 MPa. So, line pressure here also cannot remain always fixed. So, the line pressure, exit line pressure will be something which will be varying between 1 MPa to 4 MPa to 1 MPa, but always this what is leaving is saturated vapor. So, we can argue that for all practical purposes HE is roughly Hg1 plus Hg2 by 2, average of Hg between state 1 and state 2. This is a very important assumption. So, I am putting an asterisk here. If you do not make this assumption, you cannot proceed further because you have no information on state E. You need to have an information on state E. So, then with this information let us write the mass balance and energy balance. this is your control volume. Okay. So, what is ME? It is something which is there, M1 and M2 there is no MI, right. First law USUF. Okay. So, heat transfer is 0 because it is insulated, work done is 0 because this is rigid tank, there is no MI. So, this term is 0, neglect changes in kinetic energy and potential energy. If you do all that, of course, here also although it is not relevant, but still. So, you have M2 into U2 is equal to MEHE sorry minus MEHE plus M1 U1, right, and minus ME is M2 minus M1, right. So, U2 we require to find out what is state 2. So, U2 is okay. So, let us write now. We know what is M1 and what is we know what is M1, but we do not know what is M2, right. So, M1 is what? So, whatever we know, let us write V by V1. So, this we know. M2 we do not know what is it, but we know this is definitely 1 minus x2 into Vf2 plus x2 into Vg2. It depends on what is x2, that what will be the value of M2. V is fixed. U2 is 1 minus x2 into Uf2 plus x2 into Ug2. Okay. So, this equation let us write M2 is V by 1 minus x2 into Vf2 plus x2 Vg2 into U2 1 minus x2 into Uf2 plus x2 Ug2. So, this is the left hand side is equal to M2 into He, M2 into He is again V by 1 minus x2 Vf2 plus x2 Vg2 into He plus m1 into U1 minus He. U1 you know from table state 1, U1 is Ug at P1 because quality is 1 and He is this approximation. So, this is an equation, this equation where you have everything known except x2. So, from here you can solve for x2. What is x2? So, if you solve for x2, x2 will be 0.7936. Okay. So, if you solve for x2, then you will immediately find out what is m2, because m2 is a function of x2. So, then what is me is nothing but m1 minus m2. Okay. So, me is equal to m1 minus m2, this is 27.24 kg. Okay. So, again this is quite an involved problem where by using the energy balance you are calculating the quality of a state, right. It involves both mass and properties. So, to summarize, we have discussed so far the basic concepts of heat and work and also the first law of thermodynamics, considering energy transfer of through heat and work for control mass system and control volume undergoing steady state process as well as unsteady state process. So, that brings us to a junction where we have got a basic feel of how to apply energy balance in the purview of the first law. But all processes which satisfy the energy balance may not actually occur in practice. So, what inhibits those so called unrealistic or impractical processes to occur despite satisfying energy balance? We will consider or take that up in our next lectures. Thank you.